To be honest with, okay. Hi everyone, welcome to today's Silo. It's my pleasure to introduce Professor Sujay Sanghavi, who is here visiting us from UT Austin. He's the Betty Margaret Smith Professor of Engineering in the ECE department there. He has also been an Amazon research scholar and research scientist at Amazon for a few years now. So, he has worked on a lot of very interesting research problems in foundations of machine learning. Early on when I was a grad student, I became familiar with some of his works at that time in sparse recovery, low rank matrix completion and recovery. And he has worked on many interesting questions since then, including things like self-distillation. And as we have now are in the era of LLMs, he's been looking into a lot of interesting questions in the space of LLMs. So it will be too long for me to list all his accolades. So in the interest of time, I'm going to pass the baton on to Sujay to tell us about diffusion language models. Thanks, Sujay. Take it on.
Okay. Thank you so much for everybody for coming for for my talk. And thank you so much to Ramya for inviting me here. We had her over, I think, last week at UT. And, so there's definitely very cool work going on here at Wisconsin as well. I have also, been here in this room many times, so it's always a pleasure to come back. And so, as Ramya pointed out, I started working on language models. I presume I'm not the only one. I think everyone has started working on language models. But what this is not your usual language model. It's kind of a weird language model. It's not as good as the actual language model, but I think it's a good research area, and we can try to work to make it better. Okay, and so I'll tell you what diffusion language models are for those of you who may not already be familiar with it. Okay, so I'll present two pieces of work, and the first one is done by my student Parikshit at UT on joint sampling. And the second one is by an intern at Amazon. He was an intern last summer, Huasheng. All right. So I'm going to go brief intro, and I have like pretty sparse slides, and they're mainly pictures. So I'm hoping people stop me, ask me questions, and so on. Right. So just raise your hand or just say excuse me or whatever. Okay. So let's start by recalling autoregressive language models. I think most of you are already familiar with what it is, but just to set up notation and set up pictorial notation, I will go over this. Right, so I'm going to represent a language model this way, where like going from top to bottom is going along the sequence, and going from left to right is going in time. So I'm like doing a forward pass, like I'm doing an inference pass if I go from left to right, and I'm going down the sequence if I go from top to down. So we can ask a question: what is the weather? We put that, and so there's a sequence of tokens that become a sequence of embeddings, which goes into this like transformer, which has causal attention, which means that this output depends on these inputs. It makes a final embedding, and then that embedding goes into a language model prediction head, which maps it to a probability distribution over the set of all tokens. And then from this probability distribution, we sample the next token. Right? I'm just reminding us how language models work. Right? This is how they work, and this is what these pictures mean. Right? Like, these are the tokens, these are the token embeddings, this is the transformer, this is the output embedding, language model head, output probability distribution, right? And so the way inference proceeds is we will sample from this distribution. Maybe we get the word, we'll get a token ID. Let's say the word is it. And then we do the same thing again, but now we feed it in and we get another one, right? And we have a different distribution and we sample it again, we get is, and yada, yada, right? So this is how autoregressive language models generate language, right? And so, we can associate like a probability distribution notation to this process by saying that, every subsequent token is conditioned on the things that were input to the model, which in this case is X, which is, what is the weather, y1, which is it, and y2, which is. Right? So at every time, it's sampling from the correct conditional distribution going forward in time, going forward in sequence length. Okay. All right. So what are some issues with this, right? So autoregressive models are, slow to infer because it's highly sequential. You have to do like this one token at a time. So potentially slower than doing multiple tokens at a time. And the other thing is that it's causal, right? Like I generate the first token, I generate the second token, and then I generate the third token, and maybe the third token, and by then I realize that I'm on the wrong track. There's no real way to backtrack, right? Like you kind of stuck with what you started with, right? And so both of these are kind of underlying motivations for why don't we generate multiple tokens in parallel and in any order, right? Either in parallel or in any order, right? Like it would be cool to have this kind of a flexibility, right? Now, standard autoregressive models do not have this flexibility for multiple reasons. One of them is causal generation. The other one is like how they're trained and so on, right? But this is this was the motivating question for thinking about diffusion language models. Okay, so for those of you who were maybe paying attention to language models before GPT came out, this is very familiar. This picture is very familiar. This is the BERT model. And so let us remind ourselves of what the BERT model is. Right? So the BERT model, I think, came out maybe in 2017 or 2018. I'm not exactly sure. And it's a non-generative language model trained, pre-trained with a slightly different task than next token prediction. It is missing token prediction or fill in the blanks, right? And it's called mass language modeling. And so the way the BERT model is, so the BERT model is a transformer, but with full bidirectional attention, right? That means the output embedding of, at the first position depends on all tokens, not just the first token, right? And the way it's trained is you take a sentence from your pre-training data, like this is a sentence from the pre-training data, and then you just block out or, mask out two positions. So you have a special token, which is the mask token. You just mask out two positions, and then you try to predict what these positions were from the data, right? So, this is the output embedding, this is the loss, this is the language model head, and then you put a loss between the output distribution of this language model head and the ground truth, right? And BERT is trained in this way with 4 or 5 different masking patterns. There's span masking, random masking, yada, yada. But, at a high level, BERT seems to be the solution to our problem, right? It can, like if I give it an input string like I had in the previous one with a bunch of blanks, BERT is literally trained to fill in those blanks. So why don't we just use BERT and call it a day, right? This is the first thought one would have, right? And okay, so just one more thing. Let's remind ourselves of the probability notation. And I keep reminding ourselves because we'll come back to it, right? So what is BERT doing here, right? So let's say I have x4 and x6 masked out, and I'm trying to predict it. This output probability distribution is the probability distribution of x4 given xu, which is xu is what is currently unmasked, right? And x6 is x6 given unmasked. And so, in BERT's pre-training, right, we want px4 to be correct, x4 given xu to be correct, and separately, we want px6 given xu to also be correct. Okay. Yeah.
How, like in a sentence, how many could you mask? For example, this example you said, oh, I'll give a few and then mask the rest. Would that actually work? Versus like when they're training, is there a limit on how many things they mask?
Yeah. So that's a great question. So the question is, if it's trained this way, would it work with the full span out? Maybe it would, because one of the, like BERT is trained with many different masking patterns, and one of them is span masking, which means you take a span and mask it out. So potentially it could work, right? But yeah. So so XU, like in this talk we'll see XU again and again, and it means the number of the set of unmasked tokens that you have put as input. Okay, so this is the idea. Let's use BERT for parallel generation. Let's put in our tokens. Let's do a forward pass with BERT. BERT's been trained for this, so it will work. it doesn't really work so well, right? Like one forward pass does not work so well. It's not very accurate, right? Because so we wanted to become more accurate, right? Like our notion of accuracy has changed by what autoregressive models can do, and we want to be much more accurate than what BERT is. Given that BERT can only do this, what should we do? Any ideas? For people who don't already work on diffusion models. Okay, so let's step back a minute. And BERT, the way I just said it for text strings, is like what GANs or generative adversarial networks were for images, right? If for those of you remember what GANs are, right? What GANs do is they take a noise vector and they map it to images, right? You do like one forward pass to the model and you get an image, right? And GANs are no longer the state of the art in image generation. They've been replaced by diffusion models. And what is the difference? Diffusion models also start from noise. Okay, so now we're in image space for a bit, okay? Diffusion models start from noise, generate something, but then you don't declare victory. You instead like use that output to make a slightly less noisy input. And then you do a forward pass again, and then you do a forward pass again. And so for the same set of parameters, you're doing multiple forward passes to generate a single image, right? And that is much more accurate than a single forward pass through a GAN, right? So BERT for text strings, as I just said, is kind of like GANs for images, and diffusion language models are like diffusion models for language, right? Like I think it's doing for language what I just said for images, right? The repeated inference passes with progressively less noisy inputs. Okay, so this is the background. There has been an increasing amount of work on diffusion language models. I think it's fair to say diffusion language models are still in their infancy as compared to autoregressive models, right? So, this is just like a little infographic with only dates. The X and Y axes don't really mean anything, okay? On the left-hand side plot, but it shows you that like many different companies and universities are trying many different styles of models, like discrete models, continuous models, multimodal models for diffusions for language. I'll just mention one paper, which was LADA. This was, I think, maybe early this year or late last year, which was an 8B model that had the same, zero-shot downstream accuracy on a bunch of tasks where many of us are familiar with, which is GSM 8K, Truthful QA, MBBP, and so on, as Llama 8B, right? So it was a model of the same size as Llama 3, and it had similar or better performance on all these models, on all these benchmarks. So at least from a parameter perspective, there's some kind of equality at the 8B scale. Right now, obviously, Llama 3 8B is nowhere near the boundary of autoregressive models, right? The autoregressive models can be made much bigger. Diffusion models, people are trying to make them much bigger and so on. But you kind of get the idea of where it is right now. Any questions? Okay. So, one of the things driving interest in diffusion models is that they're well suited to tasks which may require like planning and consistency, right? So besides language, people are quite interested in it in robotics or for any other such planning tasks. Right. Okay. Mass diffusion language models, this is a little infographic about how they work. So let me go over it slowly. So it unmasks a few tokens in each inference pass, and then feed these back into the input, right? Less noisy here means less masking. So this is the input we start with, right? And as I said, when I go from left to right, I'm going forward, and I'm going forward in time, right? So we have this token string, which becomes a sequence of embeddings, goes into a transformer, a sequence of output embeddings, and then you have some possible tokens, and then you commit to two of them. Typically, you commit to the high confidence tokens, and you can measure confidence as minimum entropy or like how sure the most sure token is or whatever, right? And you have various notions, and you just pick one of them, and then you pick some tokens and say, I'm going to commit to these. So you put them into your next input string, and you repeat this process And so this is showing, for example, 2 tokens at a time being generated in the as you go forward, right? So every forward pass of the model gets you 2 tokens, which is in theory at least twice as fast as an autoregressive model. Okay, and it also, as you can see, allows for any order generation and multiple tokens. So this is a solution to our motivating problems, right? In some sense. Okay, so what is the problem? Like, why are we not done here? The problem is that parallel generation sucks. Okay, it's pretty bad. The accuracy drops pretty quickly. Right? So here I took, we took a Dream 7B model. So this is a diffusion model that started with Quen, which is a state-of-the-art autoregressive model, and made it into a diffusion model by an enormous amount of post-training. But it's now, as at least in open source models, a state-of-the-art open source diffusion model, right? And so this is just training free. Yes.
Oh, sorry, I thought you were going to slide on.
No, I'm still here. Okay, yeah. So what this measures is NLL is the negative log likelihood. So lower is better, right? And on the x-axis, I have like k equal to 1, 2, 3, and 4, which means 1 token at a time, 2 tokens at a time, 3 tokens at a time, and 4 tokens at a time. So you see that log likelihood is getting worse. MOV is a score that basically measures how natural linguistic is your language output. And here higher is better. And we see that MOV drops pretty significantly. This is like zero-shot downstream eval of MOV, BBH is big bench hard, which is and then MBPP, math, GSM 8K is I guess also math, right? And the outside, so this is a radar plot. Like for those of you who have like swimmers in your family, you would have seen this plot maybe, right? But this essentially, the further out you are on the axis, the better you are on that on that task. And the big hexagon we have here is dream at 1 token, so slow dream, right? Which is like 1 token per unit time, and this is 4 tokens per unit time. And you see the drastic drop in all kinds of accuracy. Yes.
So the way you described it, you fix like a number of tokens to generate stage 2, for example.
Yeah.
And you pick those 2 which have the most confidence. You could also imagine just a threshold on confidence, and then maybe sometimes you just take 1, sometimes you take 4, depending on how confident those generations are. Would that improve anything here?
No, not really. So all the variants you can think of, right, which is have a fixed number of unmasked tokens or have adaptive unmasking, threshold-based unmasking, and remasking, and everything has been studied, as you can imagine, right? Yeah, and they all help in their own ways, but it's not very significant, right? Like there is a fundamental issue with this setup, which we'll go into. Yeah.
The thing with just 1 token, that's again just taking the most confident one of the.
Yeah. So you have some.
You did it like just autoregressive. You generate all of them, but you only keep the first one that came right after the text you had.
So you don't even need to generate all the others then. If you knew you were going to do that.
To do it. I mean,
so then you're autoregressive, except you don't have causal attention.
Yeah.
That will be like autoregressive. Yeah. So there is an intermediate called block diffusion, which does the leftmost block at a time. Which is useful if you want to use diffusion models in chat mode. Yeah, there are all these variants. They've all been tried. Yeah. But in all of them, so like Dream uses minimum entropy as its selection criterion. You can use some other selection criterion. They all have this problem. Yeah. Any other questions? This just shows that one of the 2 promises is not really a promise, because you get a really like a much worse language model than what you hope for, right? Like this advertisement plot from the Lada paper, this is with 1 token at a time. Okay. Right. So at 1 token at a time, it is comparable or better than Llama, but actual inference cost of 1 token at a time Lada is much more than actual inference cost of Llama 1 token at a time, because in autoregressive models you can reuse past compute by KV caching. In diffusion models you cannot do that. Okay. All right. So why is this happening? Right? Why is this happening? Right. So one is, of course, we're doing less compute, so you got to have less accuracy. Okay. But there's another reason for it. Right. And so let's go back to autoregressive models and see why they're so good. Right. So as I mentioned, in autoregressive models, and let's say we're just now we're just doing like just straight up generation, okay, without an input. I want to generate T tokens, and at every time step, I am sampling xt plus 1 given everything in the past. Why do I say it's like this? Because we have causal attention, and because x1 to xt is already been committed to, and then I'm using that as an input in my inference forward pass, right? So this is math encoding that this stuff that's inside the given portion is what went into the input of the transformer, and this is the output probability distribution, right? And so once I apply P to the conditioning, I'm doing a forward pass. Okay. So with this, we see that the overall string is actually coming from the correct joint distribution, right? Like every model encodes a joint distribution. It may be a bad distribution, it may be a good distribution, but at least autoregressive generation as a process is sampling from the correct joint distribution represented by the model. Okay. So what is this? What is the equivalent such statement that we can make for diffusion models? Let's try to make this kind of statement for diffusion models. Okay. So let's remind ourselves how diffusion models are trained, right? Like this is true for two reasons. One is the sequential generation, but the other one, this is also how the model is trained, right? The model is trained to predict the next token in training. And so that's why when used in test, it's doing the right thing. So let's go back to BERT model, to diffusion model training. And it is kind of like BERT style training, but at different levels of masking, right? So this slide represents a single training sample of a diffusion model. You take a string from the pre-training data, you mask out random locations of it, just random. People don't do all this span and stuff in diffusion, as far as I know, in diffusion models, right? So you mask out some random positions, you put it into the model, you get a bunch of output logits and then output probability distributions, and then you take a loss between that and the ground truth. Okay. And so the only thing that changes from one sample to the other is the string and the level of masking, right? Like here I mask 2 out of 5. Sometimes you'll mask 4 out of 5. Sometimes you'll mask 1 out of 5. And you just put all of that into the model. And that way the model will learn to do the right thing at the right level of masking. Because in training, it has seen all levels of masking. Yes.
But is this kind of like going repeatedly using the same model like you do in diffusion model? So that's not done during training?
No. During training, we don't have repeated inference. During training, we take a string, we mask it to a fraction, we forward pass through it and try to predict the full string, and then throw the whole ensemble away and do this again for the next sample. What one could do is predict once and then use that input and predict again. So that's two-step training, but that interleaves inference and training. And so it's kind of painful to do. It's like more than 2x the compute. So people don't do it. Yeah.
But it's how you practically also train image generation, right?
Yeah.
You don't do the whole sequence.
Yeah. Yeah. This is borrowed directly from images. In image diffusions, you do the same thing, but except that you add Gaussian noise. Here you add mask noise. Right. So the way they're trained, you take a string, mask, unmask, throw away the whole thing, take another string, mask, unmask, throw away the whole thing. That's how they are trained. Right. So with that training, what are these distributions? What is each output? Well, each output is basically for every position. So in a diffusion model, you have some set U of currently unmasked things, right? And then for every position I, the output is the probability of xi given xu, right? Which is what do I believe about my particular position, single position, given the entire unmasking that is the input, right? Okay, because this is what it's being trained for. This is what we are training it for. Okay, so what this means is if we unmask exactly one token at a time in every forward pass, right, then the t plus 1th token that we unmask now it's not at location t plus 1, it is at some I of t plus 1, right, will be the correct, will be the correct marginal given all the past unmaskings. It will still be the correct marginal, right? And so if we do this t times, we will be sampling from the correct joint distribution, right? So one token at a time unmasking is sampling from the correct joint distribution. However, if we unmask 2 tokens at a time, we are we have gone, off topic, right? Because if I now have 2 positions and I try to unmask both of them at the same time, I am sampling from the product margin, which is not the true joint. Yes.
But this distribution is the distribution of the model, and in this case, your model is saying we'll have this factorized structure. I mean, I guess I'm still kind of like, what is it, I get it that it's going to be factorized.
Yeah.
But you're just saying we don't want it to be factorized.
I'm saying that
there will be other ways to work around it.
Right. Yeah. So I guess what I'm saying is that in autoregressive models, when I sample the second token, it knows the sampled identity of the first one. When I'm sampling here, the second token does not know the identity of the first one.
Just
because they are done in parallel.
Two
separate heads.
Could just have joint bivariate heads or something.
Can't have bivariate heads. It's pretty hard to make a bivariate head, right? Because it's n choose 2 heads, t choose 2 heads.
Like multi-token prediction, right? At the last layer, where you don't pass the token to the model network, it just literally does like a small, like you generate one and then that's fed on a single layer, and if you got
Dimitris, this is my paper. It's not exactly multi-token prediction as they do in AR models. That's a little different because the AR model, okay, this is a bit of a digression, but AR models, multi-token prediction has the same problem that I do, which is that they all generate a bunch of new tokens in parallel and they don't really inform by each other, right? This is similar to Eagle, if you know what Eagle is, which is a speculative decoder. Anyway, okay. So, yeah, but anyway, did I answer your question? Like,
I see the problem.
Yeah.
I guess I just was wondering, true joint, I mean, it could be that the true joint is just a big old factorized independent words model, which would be word salad, right?
Right.
That it could be what's being learned, right? So it's a little, yeah, it just.
Yes, it's not fully formally correct. Like what does this P even mean? We never trained for this P, so on. Yeah, this is true. Yes,
Yeah,
this is just some intuition. Yeah. Yeah, I guess another way of saying it is parallel sampling is a different distribution from 1-by-1 sampling. And under some flexibility in notation, one is parallel marginal, the other one is not. This is we are not the first to recognize this problem. Existing fixes all fall, I kind of summarized by this sentence, which is you use a fully trained autoregressive model outside as a judge, right? Now, with autoregressive models, if you want to generate from it, it is slow and yada, yada. But if you just give you a full string and you tell me like, how good is this string? That's just one big forward pass through the autoregressive, right? So it's like evaluating a string, like evaluating 1,000 tokens is the same cost as generating maybe 2 tokens in terms of delay, right? And so you can use that asymmetry to, try to fix this issue by having autoregressive models as a judge or by having autoregressive models as a selector for which token to select, right? So the fully trained separate model of the same size as the original diffusion model. So now every forward pass, every denoising step is like a denoising step through the model and then a denoise and then like an evaluation step through another model of the same size. So we are not going to go down that route, but these are 2 existing works, both came out, I guess, this year in iClear. Yeah. So our work instead, is to try to approximately sample from the joint distribution itself, as I just motivated before. Okay. So here's the idea. Here's our idea, right? So on the top is standard single token generation. I have some set of unmasked tokens. I unmask the first token. I do a forward pass to the model and, unmask 1 token and then do it again, unmask second, unmask the third, and so on, according to some token selection logic. In Dream, it's minimum entropy. right? So what we will do is we'll make an approximate sampler. And what it will do is it will take in the unmasked tokens, it'll make, it'll make the next sequence, but it'll also take out some hidden state. And I'll tell you what that is. We'll put both of these into the sampler, and the sampler will generate the next token and a hidden state, and then we'll do it again and do it again, right? So our sampler is like a baby diffusion model that we're going to stick on top of our original model. Okay. So let's be a little bit more specific. Okay, so this is standard generation, one token at a time from the original model, right? So I have this model, and then I'm doing one token at a time. So it's selected this token, the third last token. Then it made a next inference pass with this new sequence, selected a token, and so on, right? So this is standard model inference. And now this is our model. So the first part is the same. We're going to keep the model frozen, right? The first part is the same. We get the new sequence. That's the same as before. But now we're not going to feed it back into the big model and start paying a cost, right? Like the dream model is 28 layers, right? And I don't want to do 28 layers again, right? Instead, what I'll do is on a token by token, position by position basis, I will take the old output embeddings. That's the hidden state. So this is what, would have gone into the language model head. But instead, I will take it and I will take the input embeddings from the new string and I'll down project them together into a single embedding of the same size as before. And now I have a single transformer block layer, right? So the size of my layer is 1/28th the size of Dream, right? And it'll make a bunch of output embeddings. I will put these output embeddings into the language model prediction head, the same one frozen as before, and get an output series of output strings. Right? These output strings, I will again have, token embeddings from the vocabulary. Oops. And I will take the hidden states as before. I'll take the hidden states. I'll take the new token embeddings, and I'll make a new set of output embeddings. Is the architecture? Any questions about the architecture? Yes.
Is the new single pod transformer also like there's an nascent? There's a left to right nascent plate, or is it also player?
Yeah, good question. The question is, what is the architecture of the single transformer block? It is an exact copy of one of the blocks inside the big model. So it's bidirectional. It's an exact copy, but it's just randomly initialized and trained according to, I'll tell you how we trained it. But yeah, it's an exact, so it is a bidirectional transform diffusion. Yes.
I suppose you could also make this adaptive to account for token difficulty. So some tokens are more difficult than others to predict, right? And that sometimes is evident by how spiky the output distribution is. So like if the model is not very sure, if your last layer is not very sure, then it's probably a good idea to loop the whole model to produce a token. When it's an easy token, when the probability is very spiky, it's probably okay to use like the small module. Okay, guys.
So okay, yeah. So that's a good question. Can you make this adaptive? So we already decode one token, right? Now, when you say spiky, do you mean that if the model was super sure in two tokens, then I would as well do that instead of doing this thing?
Basically, when you're going to predict something from your module and the confidence is low, skip and do, pass through the whole network.
Yeah, yes. So, okay. So that's what you meant. Yeah, we can definitely do that. And in fact, that's one of the advantages of having a frozen model, right? Which is that, we can be adaptive, or to say a little bit more generally, we can be adaptive in the number of times we use this this like, lightweight sampler layer, including 0 times or like 5 times. Like sometimes you might use it 5 times, sometimes you might use it 3 times, whatever. Yeah, we can definitely do that. Yes.
So basically, if I understand correctly, with the new single layer transformer block that you are adding, you're going from predicting 1 predicting 2, right?
That's right.
So basically, this cuts down with respect to autoregressive LLMs at half the time, right? So like if I generate 1,000 tokens now,
yes,
500. But
no, why? You need 500 forward passes of the big model.
Yeah.
Yes.
But why can the small one, like the single layer, generate more, or is there like a fundamental limit that it's limited to one?
No, it can generate more. I've just shown one here, but you can repeat this process again. And
No, as in like the small one. So you
so you can do parallel over here.
Yeah.
Then you would run the same problem.
Okay.
It would start sucking again.
Okay.
Yeah.
You need to predetermine how many tokens you need to generate because you hit all the, like in this example, you pick 4 mass tokens here and then you get the representation. And I really think that the compute that you save is saving the computable for token. You just compute the representation of this puzzle.
The compute that's saved is doing a pass through this white box. This white box is 28 times more expensive than this box. So it's not about the tokens. Like once I have to do a forward pass of that big white box, the memory depends a little bit on the number of tokens, but not that much.
Okay, so you compute the representation for this full mass token all at once.
All at once, yeah.
Like forward pass.
No, they're computed all at once because this is a full bidirectional transformer, and I'm just doing like one forward pass with transformer.
Okay.
They're all computed in parallel.
Every single sample when you're just reusing the representation to go through the breakout that you use.
Yeah, every layer is gone through exactly once, and all of these embeddings are computed in parallel, not in time, in parallel. Yeah.
So I just trying to understand like the little square box.
Yeah.
So it's taking the embeddings, the blue embeddings, that set of embeddings.
Yeah. Oops. Yeah.
Uh,
And this embedding. So it has it is 2D dimensional input, right? It's like D and D concat. Put it into a one hidden layer MLP, and the output is a D length embedding. That's it.
I see.
And it's trained.
Yeah. And it's done for each of the.
It's done on a token by token basis. So last embedding here plus last embedding here gives this embedding, and the first embedding here and this embedding here gives this embedding. Token by So here this prediction is with the language model head from before.
So the language model has frozen.
Frozen. Yeah.
Then what is the training part here?
The thing that is shaded, the one transformer block and the projection. Okay. Yeah. So the advantage of doing this is that now the second token I unmask and commit to is informed by the identity of the first token I commit to. Okay. So this is what it looks like. If we have 2 tokens, if we use it 2 times and generate 3 tokens at a time, right? So if we generate 3 tokens for one big model forward pass, it's like I have 2 initially and 6 mask, put it through the big model, I unmask 1 more just from the big model, put it through my small model, 1 more, put it through my small model again, 1 more. Right? Then I put it to the big model again, and I get 1 more, right? And then I put it through small model and get 1 more, and put small model and get 1 more. So this is showing 3 token at a time generation, or 3 token generation with only 1 forward pass of the big. Okay. So the original model, including the LM head, is frozen, and the trainable parameters are just those shaded things. So this is the projection layer and the one single transformer block. The single transformer block is an exact copy of one of the blocks of the original model, but it's trained from scratch. Right? How did we train? I'll tell you about that later. And then it's important to note that it's important to reuse the hidden states of the original model, right? The original model did a whole bunch of compute, right? And that's represented by the hidden states, not just the final output. And we still have any order generation, but now the subsequent tokens are at least aware of the initial tokens. Okay, so now I'm going to switch to how did we train this model? Okay, so for training, just train it to do what we want it to do is the principle. So we want to mimic full model 1 token generation. So let's do that, right? So if I had a number of unmasked tokens U, and if I do the full model in one token per step, then the first one is P of xi1 given xu, and the second one is xi2 given xu plus I, right? So this is not the product marginal because the conditioning is changed. This is actually a forward pass with single token forward pass. There's two forward passes, right? And what I want to do instead is sample the first one in the same way, so P remains the same, but I want to sample the second one using this Q, which is my baby model, and the input to the baby model is the same sequence as before, right? But also the hidden states. And the hidden states do not know which one I picked. So the hidden states are a function of xu. Okay. We want this Q to be like that P. So make a loss which makes that happen, right? Like that's our training loss, right? And so this is our training. This is a single training sample, right? We take xu the way we take, so we first generate xu, and then we generate I1 and I2 by running two forward passes of the big model. And then we minimize this loss, but only with the small model. So this is fully synthetic training. If you just give me Dream, I don't even know what its pre-training data is. I kind of don't care, right? I will just generate an entire unmasking path. So I will take Dream, start from all mask, and make it generate something, right? And maybe it generates an article from Wikipedia. Maybe it generates some math. Who knows? And I don't care, right? And then I will take that entire training path, and I will take every sequence of xu. I'll take every sequence of three things like xu, xu plus I1, xu plus I2, and make that a training sample. And then I'll do that for every subsequent triplet in my training data, in this generation path, right? And so with a few generation paths, you actually get a lot of samples, right? And you can use those samples to train this sampler head. Okay, so that's the model. I think I talked about its training and I talked about its inference. So now I'll talk about its results. Yes.
So the H is some sort of light representation of
Yes. The H is this. So when you put it through the transformer, there is an embedding that comes out which goes into the prediction head.
Good.
It is that embedding. Yeah.
So if you get the output from that small single layer transformer that you have on the bottom, right? And then you feed it.
No, wait. You mean this thing?
This baby transformer that you mentioned.
This is the baby transformer. This is just a projection head.
Okay, but if you get the output of that and you refeed it back.
Refeed it into the big model?
No, to the small square.
This one?
Yeah, the projection layer. You can now predict a third, unmask a third token.
Yeah.
Does it improve at all?
So that's what this is, right? Like here I've kind of not shown the little projection heads, but this is exactly what's happening. It's like unmasking one more and then feeding it back into itself and unmasking the third one.
So what is the... So you can do this process repeatedly as many times.
Yeah, and you'll get lower and lower accuracy, but more and more tokens for free.
Yeah.
Yeah.
Okay.
Yes. Yes. Yeah.
So when you feed that to the projection layer, you feed the last layer representation and also the new word representation with the predicted token, the green one. So
great question. No, we don't. So, okay, every step is a new word. So this is the zeroth order word when we take from the actual model.
Yeah.
This is from Dream.
Yeah.
Okay. We take the hidden state. We take the new token embeddings from vocab.
Yeah.
Concat, made it single, three-dimensional, not in the vocab. Put it here.
I see.
Get some hidden states. Now we take these hidden states and go forward.
I see.
We no longer use directly the Dream hidden.
Yeah, so when you take the new token from the vocab that you predicted, do you pick just that token or you pick the representation of all the sequence?
Of the full sequence.
Oh, no.
We do exactly the same operations for all tokens, whether they are masked or unmasked. Right? Like this is a mask, it has a vector in the vocab, pick it out. This is unmasked, it has a different vector in the vocab, pick it out.
So my understanding is that the compute you say here is that you don't feed that new token through the
Full model.
The full model. You just feed that with cap to like the last layer to do like integration and then go to
That's right.
model cap.
Yeah.
So
Yeah.
then the compute you say is basically avoid this forward pass.
That's right.
How does that compare to KV cache where you basically can cache all the previous operations?
There is no KV caching in diffusion. So, yeah, because since it's fully bidirectional, every time you unmask, your whole previous KV cache is invalid. So, don't have to worry about it. Yeah. Okay. All right. So this is how we train. So this is its performance, right? This is the same plot as before, but I added a few more things. So this is negative log likelihood, right? And parallel is the base model dream, and we see that its negative log likelihood becomes worse. Actually, everybody becomes worse as you increase more tokens. And then this middle column is when you use a helper autoregressive model is one of the baselines. Use a helper autoregressive model, which is of the same size as your original model, to help it, right? And the third one is ours, where you use this like single extra layer that we trained on top, right? And yeah, so we see that it significantly mitigates drops in performance, especially in MOB, right? So if you do 4 token per time step generation, like our MOV is like just a slightly worse, while the original model drops drastically. And the same is seen also in the downstream performance, right? So the outermost hexagon is 1 token at a time. The inside, it's actually also hexagonal, it looks like quadrilateral, is 4 tokens at a time, and we are in between. Also at 4 tokens at a time, but now in this sequential fashion. Right? So we have like significantly mitigated these issues. How much time do I have? 10 minutes? Okay, maybe 10. Okay, so on Thursday, we found out about parallel bench from University of Wisconsin-Madison. And my students said, oh, we should try out on parallel bench. I'm like, hell yes, I'm going there next week. You better try this out quickly. And so we did, right? So what parallel bench is, it's been made by you guys, so you can tell me more, but it's a series of tasks and like a benchmark that exactly measures this issue of how good parallel generation is, right? And so we tried out Dream. So, there are lots of tasks, but we only know how to draw hexagons and heptagons. So, this is just, like the left one and the right one are just different tasks, but it's basically the same picture. And so this is Dream at 1 token per unit per time. This is Dream at 4, and this is us. And so we significantly improve over 4 token at a time generation on your benchmark. And then, besides parallel bench, okay, so another thing you say is like, okay, but you have this weird architecture, like, does it actually give a, gain in throughput when you actually run it on a GPU? And so we ran it on H100, and, this is the like tokens per second. And, like as you have more tokens per second, the way you increase tokens per second is to, infer more parallelly, right? And so this is again K equal to 1, 2, 3, 4, but now we show the throughput, right? And so as tokens per second increases, MOV score, and like downstream GSM 8K decrease, as you would expect. For the original model, they decrease a lot. And for our model, they decrease barely any. Right? Like MOV decreases, very minimally in comparison. GSM 8K decreases, but not as bad. Right? So there is gains in throughput. Okay. That was the first part of the talk. No, but okay, but we already have a lot of the background. Okay, so everything I talked about so far was about enabling parallel generation, where my goal was the original model frozen at 1 token per time, right? And so that's not really that's not growing the pie. That is just making the pie more tasty. But ultimately, at the end of the day, I'm still limited by what one token per time generation can do in terms of accuracy. Right now, suppose I instead say, okay, you know what, like I'm going to unfreeze the model and I want to make the model better, right? I want to make the model better in post-training, right? And then how do I do this? So here is like a Markov chain view of what's going on with autoregressive models. So imagine we're in a world where at the top, we have all pre-training data. These are all sequences ever, right? And at the bottom, we have the all mask sequence. And let's say for now, the whole world has all sequences of the same length. What are autoregressive models doing, right? You can imagine that there is some kind of quote unquote noising step, and the autoregressive models are denoising it. So what is autoregressive noising and denoising? For every sequence, it is replacing the last token with a mask to get a shorter sequence with one mask. And then it's doing that again to get a shorter sequence with two masks, and then a shorter sequence with three masks, all the way to like the null sequence, right? So, and then if we had a probability distribution over pre-training data of like some sequences being more likely than others, then it's very easy to figure out the probability distributions of shorter sequences. You just add up all the parents, right? And then what is autoregressive training? A single sample of autoregressive training in teacher force mode, what it does is, since it's causal attention, it is simultaneously teaching the all mask sequence to predict the first token, but it's also teaching the first sequence to predict the second one, and the second one to predict the third one, and so on, right? So one sample of autoregressive is reversing this track for one of these downward tracks, right? And like for every starting sequence, there is a unique path, and if you use that sequence in training, then every subsequent pair is like a training sample of autoregressive. Okay, so this is just a Markov, quote unquote, Markov chain or whatever you want to call it, just directed acyclic graph representation or way to think about autoregressive models. Right? So this is so nice, right? Like there is some forward process. Autoregressive is and is exactly reversing the path. Like every time you choose a sequence, it is like teaching the model to go on the backward path represented by that sequence. Right? It's great. Okay, what is the similar such picture? And any questions about this picture? It's a pretty simple picture. It's just a way to think about autoregressive. Okay, what is a similar such picture for diffusion models? Now it's kind of insane, right? There are these beginning sequences, and any location can be masked to go to the next one. So if we have 5-length sequences, every node has 5 children, right? And every node at the 4th layer has 5 parents, right? Or maybe even more parents, many more parents, as many parents as the vocab, right? Yeah. So you have this crazy Markov chain that finally ends up at the bottom, right? This is what's happening in diffusion model noising. And the diffusion model has to denoise this stuff, right? So it's kind of crazy, right? And that's why it's so difficult. Okay. How are diffusion models trained? Let's remind us how they're trained. You take a sequence, you noise it to some level. Let's say here it's like a super high level, like 4 out of 5. And then you say, okay, you know what? Like that's your input. And as a model, can you figure out the full final output? Right? So go in one hop from where you are all the way to the top. Right? As opposed to what an autoregressive model expects. An autoregressive model expects that when you are at this level, you only need to figure out how to go here, right? But a diffusion model is when you're here, it makes you to go there straight away, right? It's kind of crazy, right? But that's how they're trained, right? And so we're trying to put all tokens with very little context, right? So this process, as you can imagine, is super error prone at the beginning, right? It's very uncertain initial steps, much more so than for autoregressive. Because in autoregressive, you just have to predict one next token, and you know the position of that token. Here, you have to predict all the next tokens. And you don't know which one will even be selected for subsequent unmasking. So our intuition or our thought is, let's try to make this initial inference step more reliable, right? Like, can we further train the model to make this, when it's super masked, at least help it out a little bit? Okay, that's our aim, right? So there's a generic idea in generative models writ large, which is self-training. It's this very weird phenomenon. If you have some generative model and it works, it's been shown to work in some cases for autoregressive models, also image models and so on, right? The generic idea of self-training for any generative model is use the model to generate the data, and then use that data to train the model again. And many times the new model is better than the old model. Okay, go figure, right? And there are some reasons for it. We have worked on it. It's kind of like sometimes you can find reasons for it, and sometimes you don't understand what's going on. Right? I think that's my personal view of it. But it is a thing in that in language models. Okay, so for us, what this means is, if you just want to use naive self-training, we will start from all masks. We will generate a sequence. We will use that in our data. Doesn't really solve the problem of uncertainty in initial steps. Doesn't solve the problem, right? We still have the same uncertainty. We just got more data, right? Doesn't really help. So our idea is to dive a little bit into it and make a variant, which we call calibrated self-training. And the idea is that if I want to help somebody who's basically clueless, right? Take somebody who's a little less clueless, but not fully clued in, right? And use that as a teacher to teach this. Okay, so I take a less masked sequence, put it through my model, I get a bunch of output logics, output probability distributions, and then I take the more masked one, and I make a distillation loss, which tries to make these outputs similar to these outputs. Okay, we want the clueless person to be like a slightly clued in person. And so we take the logics of the clued in person and make that the teacher for a distillation loss on the clueless person. That's the method. Okay. Yeah. So this method we applied on LADA 8B, which is another, like state-of-the-art open diffusion model, right? And so, yeah.
The idea that you're going to interleave this self-training process somehow, or when does it happen?
Yeah, good question. So we first take a fully trained LADA, and then we post-train it. Yeah, so
this is almost like some sort of regularization step, so that somehow the generated distributions are consistent across different masters and stuff.
Yes.
That way.
Yes, you can think of it that way.
So it may be one case of self-training where all you're doing is saying, you do what you do, but at least do it consistently across different masking patterns or something. Is that anything about it?
Yeah, that is one way to think about it. I think the simpler way to think about it is that, we want it to somehow be informed by, the future, right? Yes. So you're right. Like, figure out what its most likely future is, and then be informed by that future earlier on, right? Because when you are clueless, there are many possible futures, but the fact that this is a generated sequence means this is in the mode of the futures.
Yeah. And
so if I already told you where the mode of the future would be, you should like guide yourself in that direction. Yeah. Okay. So in the interest of time or lack thereof, base self is naive self-training or just self-training, and it's kind of all over the place. Sometimes it helps, sometimes it does not. These are, 3 tasks that people consider to be planning tasks in diffusion papers. One is solving Sudoku, Math 500, and GSM 8K, right? And, self-training sometimes is better and sometimes is actually worse than not doing anything to the model, right? But our method pretty consistently outperforms, self-training. And then, you could always try to SFT a model to make it better at your chosen task. And so if you SFT, everything becomes better, but our model still outperforms, even in the SFT regime. Same for, and it's the same story for human alignment tasks. So TLDR summarization is, can you generate a summary that is similar to what a human would generate? And anthropic HH is, I believe, like a safety task. So, and kind of the takeaway here is that distillation works best when the teacher is optimally more powerful than the student, right? Like, if I have a clueless student, and which has a lot of masks, and if I teach it with something that has almost no masks, it will be almost impossible to match that distribution. But if I go somewhere in between, then it'll be better for the student, right? And so we need to pick that level properly, right? Like, all right. That's my summary. I think diffusion models are very interesting. They're also very new. They're not as good as autoregressive models. We can try to make them better. I also like it because you can actually do it in academia. You can do like architecture research in academia, and you can train a 100 million parameter model and people be interested. If you train a 100 million parameter autoregressive model, people are not interested, I think. Unless you do something drastically different. So yeah, and there are also some interesting like theory questions. For example, what is the limit of parallel generation? Like if you only had a model to make joint decisions, but the only way you could access it is with marginal decisions, how far can you go? I think that's a good theory question that needs to be formulated. I'm interested in that. Yeah, I think that's it. Thank you.
Lot of questions during the talk, so maybe we'll take one question and wrap it up.
Yeah.
Have you looked at some specific examples how the diffusion language models performs? For example, take one example from DLMs or from local, and then see if ideally one of generate some important tokens first, and then try to provide
Yeah, so we have seen some traces. The thing you're talking about important tokens first, there's actually a paper, not by us, which tries to train a diffusion model so that it first generates important tokens. It's called anchor diffusion. Yeah, it does that. There's a paper on that. Not my paper, but yeah. Thank you.